So you know in the first assignment, we can only deal with some simple obstacles, typically just the circular obstacle. But for the very complicated shape obstacles, we are not able to deliver the solutions. But the Voronoi diagram and the dynamic programming techniques are much more powerful. So you can discretize the problem space. So it's potentially that you are able to deal with any complicated shapes. So in this case, we got two obstacles. You know there are only one narrow gap between the obstacles. And all the coordinates of all the vertices are given. So they are well defined here. So the starting point and the destination are given. So what you are required to do in this assignment is to discretize the problem space in order to got the nodes, different nodes and the vertices. So all the coordinates will be known after you use the Voronoi diagram, so that you can use the dynamic programming techniques to find the path with the shortest distance. So this assignment will be due in the revision week. So I try to give you more time. So you got 1 month, at least 1 month to work on this assignment. But I will suggest you to start in an early date. Because for the assignment 2, although I leave at least 3 weeks for you, but I noticed that some students only start from last week. So you know the assignments are not easy. They are not so straightforward. So please don't be so confident in yourself. So try to start early. If you got any questions, you can ask me. So you know the examination will be quite challenging because there are so many mathematical derivations. So again, if you are very confident with your mathematics, so it's okay, you can just give up the assignments. Try to get the full marks from the examination. But if you like more marks from this course, so I will suggest you to work hard in the assignment. So you know each of the assignment will help you to earn credits. So it's quite a lot in the course. For this problem, if you do the proper programming, you are able to deliver a path like this. So in the theoretical background of this method is not very complicated, but it requires more programming skills. So for me, I solved this problem by using about 2 to 3 hours to solve this problem. Here is the results. So the steps will be the marks. You know, if I show the steps to you, then the marks will be deducted.
So never mind, like, you thought a bit can really.
Okay, so these are the third assignment. So this assignment will be available on Moodle today. So shortly you can download the assignment and start to work on it. So from the last lecture, we start the topic of dynamic programming. So it's the last topic in this lecture. And in the last lecture, we use a graph example. We use a graph example to show the idea of the dynamic programming. So essentially, the dynamic programming is an iteration-based method. So it's very very suitable for the real-time implementations. So the basic idea of the dynamic programming is to solve the problem iteration by iteration or step by step solve the problem. But actually the dynamic programming is much more complicated and powerful than the graph example. The dynamic programming is a very powerful mathematical tool. So today we will give the standard problem formulation and solutions to this problem. And later we will give you some examples to show how to use the technique to solve the real optimization problems. So for the problem formulation, firstly, let's look at what are the problems we are facing. So the problem formulation is somewhat similar to the problems we are trying to tackle before, but in this case, it's a discretized format, because we are trying to use the computer to solve the problem. So again, we are trying to solve a minimization problem. So we try to minimize some cost function. And also this cost function is a scalar function. But the definition of the scalar function is a bit different. So I will explain this in details. So firstly, we have this expectation operator because we can deal with the random variables in this problem. So we have a function to deal with the final state. So it's similar to the problem formulation in the calculus of variations. Remember, we have a function corresponding to the final state. So this is the last state corresponding to the final condition. And plus the function in between from the initial state until the state just before the final state. So this function is given by this ji in terms of the state vector and the input. The input is given by a function, a control function, and we have a random variable. So all these are potentially vectors. So here we have this one scalar function. So this one is also a scalar function. So this one is also a scalar function. So the scalar functions describes the quantities that we are going to optimize. So for example, the distance, for example, the energy, the control energy, like this. So it's a general function, general objective function. So the x are the state vector. So the xn is the last state. So the xi just the current state. So we have this mu I to be a function of control policy. Control policy at step I. And this W is the random disturbance. the random disturbance, for example, some forces of the wind. So the wind will cause some random disturbance to your control problem. So these are the cost function. So this cost function is quite similar to that we used in the calculus of variation. So we have the final state function, and we have the function to evaluate the states in between. And all the cost functions are scalar functions. And here, because we have a random variable here, so we evaluate the expectation at the average, corresponding to similar to the average of the effect. So the cost function subject to the dynamics of the system. Subject to the dynamic of system. So the dynamics is a discrete problem. So we are given the dynamics given by the difference equations. So the next state is given by the state given by a function of the current state and the control input, and also the random disturbance. So we have this control input at here. So this is a control input. So the control input are linked to the control policy by this function. So we have this control input is given by a function of the state vector. So the control input is defined by a function of your state with a control policy. So we have this k equal to from 0 to 1, 2 up to n minus 1. So we define the cost function, we define the dynamics of the system. So this one defines the control input. So we want to optimize this function in terms of the control policy, because the control policy will determine the control input. So eventually we want to optimize the function in terms of the control policy. So the control policy is defined as a vector so that we can calculate the optimal control policy step by step. So in each step for each state vector, we can determine control policy, optimal control policy. And in each step, the control policy will be different. So these are the idea of the problem. From this problem formulation, you can see the problem definition is quite complicated. Quite complicated means this equation can represent quite a lot of problems. So the method itself is quite powerful. So we can deal with the different control policy in different stage, returning to different state, and we can also deal with the random variables that is caused by the environment. So these are the problem formulation, the problems that we are going to deal with. So what are the solutions to this problem? So the solutions are the dynamic programming algorithms. the solutions of say the dynamic programming algorithms. So the idea is quite similar to that we used in the graph example. So we start from the final state. You remember that when we have the graph, we define the function to represent the distance from any state to the final state. We define that to be the cost function. So we have the f. So we have the f of the final state to be 0 because it's the same node, the same location. So from that we can go back. To the previous stage, to the immediate previous stage, and we can define the fh, the fi, as to the distance from the node h of I to the destination. So we do this recursively. And in each iteration, we don't need to do the optimization that we did before. So we can use the optimal results that we already calculate. So these are the idea. The dynamic programming just use the same idea. So we start from the final state. So the final state, we have this cost function Jn. So Jn is just given by this final state function. So currently we don't know the value for this one, but in mathematics, these are the final state. Final state for the final, we can define the cost for the final state just given by this Jn xn. So these are for the final state, corresponding to our f, fj is equal to 0. So in the graph examples, these are clearly known. And in the general dynamic programming, we define this Jn equal to the final state function. So next, we can define the recursive part. So the recursive part is given by this. So the optimization in the case step. Is given by. We want to minimize. You can try to recall our graph example. We want to minimize. So remember that we have the node example like that. So we have the complicated node example. So firstly, we start from the final state. We have this final state to have this one. So next, we go back to the previous stage. So in this stage, we try to minimize the cost. So we try to minimize cost. So for the cost, we need to simulate. We try to simulate this equation, but we just make one step iteration. So the idea is to. So this is the same that copied from the problem formulation, copied from here. But the idea is we are only going to minimize the case step. And plus the optimal solution optimal solution for the next step. This for k equal to 0, 1 up to n minus 1. So these are the solutions, I would say the algorithms. So in this equation, I just ignore the random disturbance. So if you got random disturbance, you can just put it here. If you got the random disturbance. So to make it simple, I just ignore this random disturbance. So the idea, I think the first step is quite straightforward to understand. So it's just the cost function in the final state. Then this iteration, the iterative part, the idea is to minimize the function that's for the case step, And this part is the optimal solution that we already established from previous step. So for example, here we have the Jn, then for the immediate previous state, for the Jn minus 1, so we have this function, these are Gn minus 1, so these are Jn, and Jn are known from here. So the idea is that this one is known. So for the n minus 1 step, this one is known. We only need to optimize this single step. So we do this recursively. So in a graphic representation, so these are the solutions to this problem. So the equations are quite simple. But however, to use this technique is a bit complicated. It's not an easy technique to use. For the graph representation of the method, so we can understand this by using the principle of optimality. So you remember in the last lecture we introduced the principle of optimality. So the principle of optimality is fundamental for the dynamic programming. So you remember we plot the state space. So for the state space, we have an initial state x0. So these are given by the initial condition, the initial state, and assume we have a final state xn. So these are given by our final condition. And assume we already solved this problem. If we already solved this problem, so we know the optimal trajectory, so we know the optimal path going all the way from the initial condition to the final condition. And assume this one corresponding to the optimal trajectory, so the optimal path, giving you the optimal cost. So this idea is to start from the final state. So we start from the Jn, from the final state. So the final state just given by this function. So this function is already defined. And from here, we're going back to the previous state, going to this n minus 1. So for the n minus 1 step, this j, k plus 1. So if the k equal to n minus 1, then we have this k plus 1 equal to n. So the k plus 1 equal to n, so this one will be given by this one. So this one is known. So because we already defined this one, so this one is known. This one is known, so we only need to tackle the optimization in this step. So it's a one-step optimization. So we only need to optimize the function for the step of n minus 1. So we do this recursively. So we do this backwards. Recursively until we go to the state of k. So for the state of k, then the next step will be k plus 1. And the step of k plus 1 already solved from all the previous iterations. So we assume already known. So we only need to do the one-step augmentation. So we do this recursively until we arrive at the initial state. So these are the idea behind the dynamic programming. So for this iteration, actually we can prove it with mathematics. With simple mathematics, we can prove this equation. We can do a simple proof for this equation. So assume we are looking at the state of k. So we can define this cost, this j k, corresponding to the state xk. So assume we already solved this problem. So it's an inverse problem. So we assume we already solved this problem. So we know the minimum cost. So assume the minimum cost from the kth state to the final state. So this is defined by the jk. So this one defines the cost function. From, because here we have the k, from the kth step to the final state. So we define this one is the cost starting from the kth state and go all the way to the final state. We define this to be jk star. So this jk star is given by, from our problem formulation, we know this one is given by, so this one is just a copy from the problem formulation. So the final state, gn xn and plus. So originally we held I starting from 0, but now because we are starting from the state of k, so this one should be k from the state of k to n minus 1. The equation are supposed to be the same.
不用，被玩我。
So this equation are quite similar to our problem formulation. So we only change the
Just happy
starting state from 0 to k, because now our starting point is the kth state. So this function will be minimized or optimized in terms of the optimal policy at the kth step and the k plus 1th step, and all the way to the n minus 1st step. So we use this set of optimal control policy from the step k to step n minus 1 to minimize this function. So this equation can be given by so we have this Jn, so I just ignore the dependence on the state to make it easier to represent. So the Jn plus, so in this function, I just divide this function into two parts. So for the I equal to k, so we have this jk plus the remaining part. The remaining part will be I from k plus 1 to n minus 1. So in this equation, I just divide the summation in two parts and take out the first equation of gk. So this from k plus 1 until n minus 1. So for this equation, we may divide the equation. So the first one is just containing this jk. So for this jk, the optimization will be in terms of the control policy, the optimal control policy in the kth step, and plus the remaining part. So the remaining part will be this Jn, the final state, and plus the summation from k plus 1 up to n minus 1. So this one will be optimized with all the optimal control policy from k plus 1 up to n minus 1. So now we know this one can be given by this one-step iteration. So this becomes one step. One-step iteration, and this one is just the optimal solution in the case step. And this becomes our jk sum. So here we provide a simple proof of the dynamic programming algorithms. So for the dynamic programming algorithms, so the first equation will be this one. So the final state for the Jn is equal to the final state equation. And the second equation will be the iteration, for the iteration. And in the iteration, we only need to make one step optimization. So that means we start from the final state. We start from the final state. So you just think about the graph example. So we start from the destination, and we keep solving the problem backwards. You remember that we start from the destination and we keep solving the problems stage by stage and backwards. So these are known as dynamic programming. I would say the backward dynamic programming. So here are the problem formulation, and these are the algorithms. And we also provide a simple proof for the algorithm. But now the problem is how to use the dynamic programming algorithm to solve the real problems. So the idea sounds interesting and not complicated. So we just make the iteration and do the optimization step by step. But how to use the technique to solve the real problem? So let's look at an example. So the example is similar to our dynamic programming formulation. So we want to optimize a scalar cost function. So this scalar for cost function is defined by two parts. So the first part is the final state, and plus function represent all the intermediate state from 0 to n minus 1. So this function is given by this xi minus 2 square plus ui square. So we want to minimize this function in terms of the control input of this uk. So this is subject to the dynamics of the system is given by this xk plus 1 equal to xk plus uk. And we also have an actuator constraint. So the uk should be between minus 1 and 1. So before we tackle this problem, so you'll notice that so here we don't have the initial condition. We don't have the initial condition. So it's something different from the previous problem. So actually, the dynamic programming is more general, so it can deal with the problems with any initial condition. So remember that in the problem formulation, you are going to develop an optimal control policy. So this optimal control policy can determine your optimal control input, depends on your initial condition. So that means this optimal control policy can take the initial condition as an argument to determine the optimal control input. So from the the problem, we can make some simple observations. So firstly, we don't have the initial condition. No initial condition is given. In this problem formulation, if we try to simulate the solutions, and here we can see the final state. The final state function is given by this xn minus 2 square. So this corresponding to the final state function. And the function in between is given by, so this xi minus 2 square plus ui square. So these are the observations that I made from the example. So to make the problem simple, we also define the n be equal to 1. So to make it simple, otherwise the problem could be quite complicated. So if we define the n equal to 1, we can solve the problem with the dynamic programming. So the first step, we know the first step is have this final state equation. So for the final state, we have this k equal to n, and in this case n equal to 1. So we have this j n that's equal to j1. So this given by this j1 is a function of x1, So from this equation, we know this one is given by x1 minus 2 square. So these are the optimal solution, I would say the optimal path for the final state. So the next step will be to deal with the optimization backwards. So the previous state will be k equal to n minus 1. So the n equal to 1, so this one equal to 0. So we have this jk. So the k n equal to n minus 1. So this equal to n minus 1. So this equal to j 0, n minus 1 equal to 0. So this one is given by, so based on our dynamic programming algorithm. So this one is given by the function for the current state. So the current state is 0. So the g0, the x0, u0 plus the optimal solution from the next state. So next state will be g1, x1. So we try to solve this problem with the optimal control policy in the state of 0. So for the G0, from this equation, we know it's given by x0 minus 2 square plus u0 square. So this given by x0 minus 2 square plus u0 square, and plus this j1 x1. So we also try to minimize this function in terms of the optimal control policy mu0. So in this function we know the x0 is the initial state. So the initial state is independent. I will say the initial state does not depend on your input. The initial state will not depend on input. The input will only determine your next state. You know, the x0 is the initial, like the initial position in the pendulum example. So the force you apply will only determine the falling state. So for this one, it's independent to the input. So this one can be moved out of the optimization. So for this one, we can just move out of the optimization. So we have the remaining path. The remaining path is given by this u0 square plus, so this g1 so this j1 x1 given by the x1 minus 2 square. So we have this one equal to x1 minus 2 square. So we try to minimize this function with the optimal control policy. So in this function, we know the u0 is the control input. So the control input is related to the control policy. And the next state, x1, will be determined by your input and the previous state, so the u0 and the x0. And from our dynamics, from dynamic equation, we know for the k equal to 0, so we have the x1 equal to x1 plus u1. So from our dynamics, equation, we know the x1 equal to x0 plus u0. So these are the equation from here. So this one equal to the x0 minus 2 square plus the remaining part. So the x1 equal to x0 plus u0 minus 2 square. So now we change the problem. We change the problem into the optimization for one step. That's for one step. So for this optimization problem, for the u0 is the control input, and the x0 is the initial state. Is the initial state. So typically the initial state will be given. So the problem is we try to minimize this function in terms of the u0. So how to solve this problem, or how to solve the general problem like this. So we just got one input. We only have one input, U0 in this case. So you know this problem is actually become an unconstrained optimization problem. So we want to find the minimizing point for this function in terms of U0. So the general solution for this problem will be to calculate the derivative. You know, we should calculate the derivative in terms of U0 for this function. So we set this to be equal to 0. We set this to be equal to 0. This will give us the general solution for U0. So when we know this one equal to this 2U0 plus 2x0 plus U0 minus 2. So we know this are equal to 0. Will give us the minimizing point. So this equal to, so these two zeros, the 2U0s plus this 2U0s, so we got 4U0s plus 2x0 minus 4 equal to 0. And this gives us the solution that this U0 equal to, so this U0 equal to 1 minus a half x0. So here we can see we get optimal control policy for this stage. And by using the control policy, also a function, we can determine the optimal control input for any initial state. So the optimal control input will depend on your initial position. So it becomes a general solution. So that's why this method is more powerful, more flexible. So we can determine the optimal control input for any initial conditions. But here we have a constraint for this one. So we have the optimal solution. So the condition for the U0 to be the solution is that this U0 must satisfy the activator constraint. So this U0 must be between minus 1 and 1. So if the U0 calculated by this equation satisfy the activator constraint, then this will be the solution. But however, if the U0 calculated by this equation doesn't satisfy the activator constraint, remember we have the activator constraint. So if this one doesn't satisfy the activator constraint, then this one will not be the solution. So we need to further discuss this. So there are several scenarios for this one. So the first one is for the U0. We know the U0 is equal to 1 minus a half x0. So the first situation is if the u0 is between minus 1 and 1. So if the 1 minus a half x0 is between minus 1 and 1, so we may further expand this equation. So we have the half x0 minus 1. This should be between minus 1 and 1. So this is equivalent to a half x0 just plus 1 to both sides. So it's between 0 and 2. So that means the x0 is between 0 and 4. So that means if the x0 is between 0 and 4, so we have this optimal solution to be 1 minus a half x0. So you know the x0 is the initial state. So for example, in our pendulum problem, the x0 is the initial position. So if your initial position satisfies this condition, so the optimal control will be given by this equation. So the optimal control will depend on your initial position, the initial state. Or more generally, the optimal policy in the current state will depend on your current state. So you know this are x0. But if we have xk at here, in general case, if we have the uk at here, then the uk star will depend on the state of xk. So today we just stop here. So we will further discuss this example in the next